Hello, random viewer, and welcome to a bit of a departure from the normal. After my previous aerodynamic analysis of the aircraft I'm trying to build, this Cheryl Dickey E-Racer, I got several questions on how to perform a computational fluid dynamics study, at least the way that I did it. I want to say that I am not an expert. I don't know entirely what I'm doing. I was just able to find a few different resources that showed how to use programs, and those programs were able to give results that made sense, at least based on numbers that Mark Zeitland had published in his study. It is very important that the results of a computational fluid dynamic, or CFD, analysis are compared to real-world numbers, and that was the method that I used to get the results that I did. I was taking all of the numbers that my analysis gave me and referenced them to the real-world numbers, and used that to figure out how changes might affect airspeed and a few other parameters on the aircraft. I also want to say that I gave a pretty simplified definition and explanation of interference drag. I have since learned that it is a far more complicated topic than I originally believed it was. Just Google Mike Arnold. It is amazing how much debate still goes on in what really constitutes interference drag and how aircraft design can be improved. It's impressive, so I have really just stepped into this world, and I apologize if I was not able to explain things to the caliber that certain people have requested that I be able to. Uh, this is new to me. I'm learning, so I will show you what I did. I'll show you how you can do a study of your own if that is something you're interested in, but just please take all that with a grain of salt. I would not recommend betting your life on the numbers and the process that I've made. It's just helpful and gives a rough ballpark idea of some of the improvements that are possible to an aircraft design or changes to an aircraft design when they are linked to real world figures. I had that advantage with the paper that I found with Mark Zeitland. Not everyone will have that, and even with it, I'm still not entirely convinced that my results are perfect. Even so, I am convinced that they're safe, and I am willing to try them out on the airplane that I am building. With that huge disclaimer out of the way, let's open up FreeCAD. This is the first program that I used. I'll be linking several videos that I used to learn how to use this program, how to install it, how to set up the add-ons, because FreeCAD on its own does not have the ability to do a CFD analysis. You have to install add-ons, and there's a process for it, and these other videos explain it better than I could, so I'm going to leave it to them. If this is something you want to do, please watch the 3 videos I have linked in the description that other people made because they are extraordinarily helpful. So what I am doing here will be a summary of what I learned from those 3, as well as what I've learned along the way. So let's go through the process. When you first open the program, it looks like this after you've installed everything. What we need to do is create a new project or whatever it's called. So I click the Create New button. Now what we need is our 3-dimensional model of the aircraft, a wing, whatever you're wanting to study. One correction I do need to make from my previous video is that FreeCAD can handle the entire airplane. I just saw some things that concerned me. I'll pull that up to show what I was talking about. So if I import the aircraft here, I was very concerned about these random faces that show up on the airplane. I'm not sure if this is here's another one. I'm not sure if this is a FreeCAD problem or my export method problem. I created this model in SolidWorks, and it would be worth trying to export only the external geometry of the model. I did not do that when I created this step file or STEP file. So that could be part of the issue. My SolidWorks subscription has since expired, and I don't really see the need to renew it right now. I've learned what I needed to. So we're just going to stick with what we've got. But anyways, whether you have an aircraft model that you've made in your own program or made one in FreeCAD, I'm sure it can be done. I just haven't learned how to do it. You're going to import that into the program. But despite those issues, an analysis runs just fine on the full aircraft. So I was able to get that to work with a lot of tweaking. It's a much more detailed model in that a much larger surface is being analyzed. So it takes some fiddling to get it to work. The analysis takes much longer, and if it takes too long, it tends to run into errors. So you really have to be careful about how you balance out this program. It's very finicky, but it can work with some tweaking, and so it takes some patience. So I'm going to click the Create New button. Then I'm going to click File and Import. Navigate to where you've stored your file. Let's just do the basic wing that is detailed in the plans for the E-Racer aircraft. So I'm going to import this STEP type file. And here we go. For whatever reason, it orients the wing straight up, which is not what we want. That's not how it flies through the air. You could try to figure out how to make it work like this. There is a way, but it just makes me unhappy. So I click up here on the top right, just on the right view, and now I can see how this looks. Now if your wing imports weirdly, you might need to click a different view, but find a view that orients, that would allow you to rotate it the way that you want. Next, it doesn't really let you right click on the thing itself, but if you go over to the design tree, I think is what it's called over here on the left, right click, transform. Set the increment here for rotation increment to 90 degrees, and then grab this red one or whatever and turn it. And there we go. Now we have the wing oriented the way that it would fly through the air, well, assuming zero angle of attack. So here's what was missing from a lot of the videos, and that's how to test different angles of attack. Well, you're going to right click here, transform again, set your increment to whatever angle of attack you want. I did 2 and 8 degrees, but let's do 3 for this one. Let's do something new. So we'll type 3 degrees in there. We'll grab that red one again, and we'll very carefully drag till it just ticks one time, like that. Now we have set a 3-degree angle of attack on that wing as it flies through the air. We'll click OK. And now we need to create the box or the wind tunnel through which air is going to flow around this wing. So to do that, you're going to click this drop down right here, Start, go over to Part. Now we're going to click this yellow button to make a cube. It makes this tiny little cube that hides over here at the origin. That's not going to work too well for us, but we can right click on that cube, edit cube, and now we can type in some numbers. So at least for this, I found numbers that work. I'm just going to type those in. I did it in yards, so you give it a length, and that makes it wider. I don't know why the length does width, but whatever. And then width does length. It's really annoying, but fiddle around with these. Get the cube to what you want it to be. I guess it's not a cube anymore. Don't forget to type in your unit if that's what you're doing. You can see I'm making this cube a lot bigger. I found a sim scale reference when I was doing this initial study on what to set the mesh size to. Our mesh is like our wind tunnel. And I do not recall exactly the rule that they used. I think it was something like 8 to 10 wingspans long on your cube. There we go, now that I've actually set it correctly. And so many wingspans your width and so many wingspans your height. I'm not perfect at making a mesh. I had a lot of people tell me I was doing it wrong, and yeah, they're probably right. I probably was doing it wrong and probably wasted some processing power, but I'm okay with that. It's hard to find a good resource on what to set your mesh size to, so I found one and I stuck with it because it worked. So there's a lot of that, just doing what works. Okay, so now we have the cube the right size, and I don't remember how I found that, and I wasn't able to find that resource again with a quick search, and I wanted to get this video out while I'm working on another, so you can find your own resources for the proper mesh size for your aircraft. Now we need to set the location, so set that however you like, but you want your wing or your aircraft to be on the edge of this cube. When I did the whole airplane, I just embedded it in the center. I did the whole thing. There is something to be said of doing only half of it and then just doubling all your results. That saves a lot of processing power. I chose not to do that for a few reasons, but we're just doing a single wing here, or a section of a single wing. So we have it sticking out just a little bit. We don't want it in the dead center though. more interesting things happen with the air behind the wing rather than in front, so it can be pretty close to the front where the air is coming in. And you can see I put it about a quarter of the way back, so we still have 3/4 behind and about 1/4 in front. There's a little bit that happens to the airflow in front of the wing, but it's a whole lot less than what happens behind the wing. So that's how I figured that out. And then as for the position up and down, I just put it not quite in the center, just a little bit lower. There's a bit more that happens above the wing than below, but there's a decent amount of both. So close to the center and then down just a little bit is going to be a good spot for that. You can see I didn't do this super precise. So again, my results are not perfect. They were good enough for what I wanted to learn. So that's why you want to be very careful. Anyways, now we have our cube set. This is our wind tunnel now. If I click on the wing like that, you can see it embedded in there inside our wind tunnel, or mesh as some people call it, because when it's a virtual wind tunnel, it is a mesh. Well, not a mesh yet. We're going to turn this cube into one. Now the next thing we need to do is cut this wing out of this cube. If we just left the two objects, the program would not know what to do with it. So we're going to select the cube, just click on it, then hold the control button on your keyboard and then click on the wing or the airplane, whichever you're doing. If you do it the other way around, where you click on the wing and then the cube, it's going to cut the cube out of the wing, which is not what we want. We want to cut the wing out of the cube. So the cube is the thing that we're cutting. The wing is the thing that we're cutting with, is our cookie cutter, so to speak. Now we're going to click this button up here, cut. Now we can zoom in and see what this did. It made a hole that exactly matches the shape of that wing inside the cube, or box at this point. Now for this next step to work, you have to have the add-on CFD Open Foam installed. So we've just used FreeCAD to set everything up. Now we're still going to stay within FreeCAD, but we're going to move into the interface where FreeCAD starts talking to this other program, CFD Open Foam. So we're going to click on that on the drop down. So we were in the part menu, and when you install CFD Open Foam, it makes it a new option on your drop down of tools. Now we're going to click this first button right here. We're going to just make a new computational fluid dynamic analysis. There we go. Our cube now turns transparent. You can see the wing inside the wind tunnel. It's great. We're going to click on this little arrow, get a drop down, and we need to verify that everything is correct inside of these. So physics model, double click it. Time steady is good, single phase is good, incompressible is good, laminar flow, viscous, that's all great. Basically, how I remember this, all the boxes on the left, make sure all of them are selected. And gravity, I don't want to mess with the force of gravity. There's no need to do that. So all those leftmost boxes, that's going to be good. We'll click OK. Fluid properties, we want to do air, not gasoline, air. Our wing flies through that. So there we go. We have set air. And I guess we could change the density if we wanted to simulate a higher altitude than sea level, but I don't really want to do that. So we'll click OK. Initialize fields. You want to do it from potential flow for velocity and pressure. By default, pressure is on this use value from boundary. You want potential flow there. Now we're going to click on the CFD solver. Don't double click it, just click it once. For whatever reason, on my setup, this parallel feature right here causes errors. This is using all of the cores in your CPU, or the central processing unit of your computer. When you set this to false, it will only use a single core. A lot of programs are single core. This theoretically can do multi-core, but it hasn't worked for me, so I set it to false. We need to make sure that we have this solver selected. You don't want that selected, it's just that one. If you accidentally drag this outside of this CFD analysis to where it's its own thing in this tree, that's a problem. You don't want to do that, so be very careful where you click. It's very easy to mess this stuff up. What you have selected, what you have clicked on, is all very critical here. So click on that solver, make sure that it is highlighted blue like that, and now we're going to establish our boundary layers. So now we're going to click on this button right here, Fluid Boundary. We want a wall that is a non-slip. Our options here are wall, inlet, outlet, and whatever those are. I have used the wall, inlet, and outlet. So a non-slip wall would be a surface that has surface friction to it, like the rough paint job of an airplane. Doesn't matter how smooth you get it, how much waxing and polishing you do, it is a rough, everything's a rough surface if you zoom in far enough. This is going to be the body of our airplane, or the wing in this case. So it's kind of hard to click in there. I guess we could select the individual faces. That would be miserable. Best thing to do is hit this button here, select from list. Select your wing or whatever. And look at that, it highlights it black. That's how you know it's a wall. And then we're going to click OK. Now we have a wall that is within our CFD analysis, and that wall is our wing. Great, we're going to click on that solver again, just once. And we're going to add a new boundary layer. Now for this one, we want a non-slip wall. Sorry, we want a slip wall. And there's no such thing as a perfectly smooth surface in real life, but a computer can model that. And that's what we want for the sides of this. So I'm going to hold the control button and I'm going to click on the top, bottom, left, and right of our wind tunnel, because that's essentially what it is. We don't want the air moving in or out of these spots. That wouldn't make sense for a real wind tunnel test. So I have selected all 4 of those, and now I'm going to click Add. So now all of those faces of our cube, and then it gets real weird when you look at it. It can really mess with your perspective, but if I go to the front view, there it is. So now we have this outside box that is now our wind tunnel, but they're slip walls. We don't want to use non-slip walls because then that would introduce more drag than what's really happening. Now we need the source of the air that's going to be blowing over this wing. So we're going to click on that solver again and make a new constraint or boundary condition. We're going to do an inlet. That's a place where air is coming in. We want uniform velocity. And we're going to select that front face right there. Just click it once. And now your speed. This is where your airspeed comes in. The unit here is inches per minute. So I calculated out, or for whatever reason, I picked 185 knots. And that comes out to 213 miles per hour, or 224,928 inches per minute. It's going to abbreviate that into 220,000 inches per minute, but that's close enough. And there we go. So that is our cruising speed of the airplane that makes sense for this particular wing. But you could test it at a variety of speeds and see how speed affects your aircraft. And now we're going to click OK. So now we have an inlet. That is where, well, we should. This is why I like to double check it. Nope, it didn't work. So click it, and I must have forgotten to hit add. There we go. So it's good to click on these and make sure that it added them properly. So we have our external walls, we have our inlet. Yes, that's looking good. Now our last face that we haven't done anything to is back here at the back of the wing. So we're going to click on that solver again, add a new boundary layer, select that, click add. That's what I forgot to do last time. So now that face there, we're going to make it an outlet of static pressure. And we don't have to do anything else to it. So now we basically have our source of air. It's going to be blasting air down this tunnel, and it's going to be going out through the back. And as that air slams through, it's going to do things to this wing. And from there, we can start gathering results, seeing how this wing is affected as it flies. Now what we need to do is click on the cut up here. And then we're going to click this button. This is the CFD Mesh. This creates like a web of shapes and points that make up this cube. And instead of testing individual air molecules throughout this entire thing, which would be take an enormous amount of processing power, it will just calculate the values at a few random points. And that's what our mesh is. So, and I hope I'm explaining that in a simple way. I know that's not a perfect explanation, but I want to make it, what I try to do is explain things in a way that makes sense to someone who doesn't have a whole lot of outside experience. Because too often people make this high-level knowledge absolutely inaccessible to those who didn't grow up with it. So yes, maybe I don't use your fancy words, and sorry, I probably got a little too angry at a few people. Comments are fun, but I'm just trying to help people. I may not give the most perfectly accurate explanation, but I'm going to give an explanation that people can understand. So that's my main goal. Anyways, we're going to put 4 inches on our base element size here. This is just the basic mesh. So we're going to calculate things that are 4 inches apart. That is terrible for a wing of this size. I don't even remember how big it is, but just at a glance from the section of it that I have in my room, it's roughly 6 feet long, this little section here. But remember, we're modeling this huge area. So this is where the idea of a region refinement comes in. We're going to do a basic, very rough calculation of everything, but as we get closer to the wing, we're going to make the mesh more detailed. So there we go. We have our base element size of 4, and that looks good. So we'll click close. Now we're going to click on this mesh, and now we can click this button right here. This is a mesh refinement. This just makes it more detailed. So if I make the relative element size 0.5, now instead of every 4 inches, when we get closer to the wing, it's going to be every 2 inches because that cuts it in half. I could do 0.25 in here if I wanted calculations every inch, and that would be a great thing to do. I'm not going to for the sake of this video because it would take a little bit longer to process. Refinement thickness, how far out from the wing are we going to be doing this? Let's go 3 inches, I don't know. Now select from list, we'll select our wing in there. So that means everything 3 inches from this surface all the way outside is going to have extra detail as the values are calculated. At least in theory. I've noticed that it makes it even larger than that for whatever reason. So now you can see we have our refinement in there. I have not had a whole lot of luck with trying to do multiple refinements, like refinements on refinements. It just hasn't worked for me for some reason. Feel free to play around with that. I ran out of patience. So this is not great, but it's not terrible either. This will give us a pretty rough idea of the lift and drag working on this little section of wing. All right, now we're going to double click on this mesh, and we need to write the mesh case. Give it a second to think. It does take just a little bit. And mesh case written successfully, that's the message you want to see. If it does not, something was selected wrong somewhere. Maybe you didn't click on the cut part over here. Maybe you didn't click on this when you created your mesh. That was an error I ran into recently. It's, like I said, it's finicky. But if you follow the steps exactly, it should work, at least for FreeCAD version 0.2. Okay, now we're going to click Run the Mesher, and this takes a while. And it starts, and we can see, yep, I don't really worry about that error too much. It just keeps on going. As long as that timer's ticking and it doesn't say Mesher exited with error, you're good. There are different kinds of programs for generating a mesh. I've had CF Mesh work the best, so that's the one I've been using. It's the default, so it probably works fine. Hey, look, another error. It doesn't seem to care. It keeps on ticking, so I'm happy. The meshing is now complete, and it finished successfully, so that is good. From here, I would typically go straight on to the CFD analysis. We have generated the mesh, but the first few times you do it, you definitely want to check to make sure it generated properly. So this is where, in this visualization part, we can click on Pair Review. And this is the first time we will use the Pair Review program. So we've used FreeCAD, we've used a little bit of Open Foam paired with FreeCAD, and now we're getting into Pair Review, which is where you view the results. So this is a 3-program tag team, essentially. And here we are. We'll let it keep loading for a second. But this is the Pair Review program. And now we can turn it and we can look around. All right, so if we zoom in, you can see these little boxes. Well, that's our mesh. Closer to the wing, we have that refinement. And if I try to look down inside there, it's, well, that didn't work. Let's see. That doesn't work either. There should be a, there we go, that's it. The view controls are always different. It doesn't really matter what program you do. The view controls always do something a little weird. But anyways, there we go. We can see that refinement in there. I'd love a little more detail than that, but I'm okay with it. And here we go. The wireframe option in this drop-down also can let you see inside a little bit better. So, yep, looks like it meshed that wing. Now we can just close out Pair Review. And here we are again. So we don't want to clear out any of this We have the mesh written, so we're just going to click close. Now we can go back to the solver, double click on that. We're going to write the case. Okay, it has been written successfully, and now we can run the solver. This will take a while to initialize, and it will start ticking, and when it's done, we can open ParaView again to review those results. And that second viewing of ParaView, where we open that program, is where we can really start calculating lift and drag as well as visualizing airflow, and there's a few different ways we can do that that are pretty cool. So I'll walk you through that when this is done. It usually takes a few hours, but what'll happen is it'll bring up a screen with residuals. Essentially, when the residuals get to a low enough value, the oscillations in the air currents have stabilized, so to speak. That's when we know the results are going to be fairly accurate, and that is when you can view them. Although, with this program, we can go straight into ParaView from any point. So if it does not stabilize, we can click stop and view it, and that's how I discovered that a 12-degree angle of attack results in a stall on this particular wing and airfoil. And now that the simulation is done, the residuals have fallen to the appropriate value for it to consider the flow stabilized and accurate enough to view, so we will review the results in ParaView, the other program. So we'll let that open. It will load for a moment, and will give us a nice red box that represents our wind tunnel that we've created. And I can move around in here, and we can see right now we have U selected. That's velocity, at least in this drop down. You can see that there is higher speed above the wing, lower speed in front and behind. Now, it's easier to see this if we switched over to the solid one, and then it gives it to us in blocks and not quite so refined. You can also change the opacity that you're viewing, and that lets you kind of see through things a little bit. Now, we can also view pressure. So we can switch it over to a pressure distribution and see that there is lower pressure above the wing, higher pressure in front of and behind. And that is part of what generates lift. There's also a little bit of deflecting the air downwards, Newton's third law, and that creates some lift as well. So that is how the wing generates lift, or at least this one does, it would seem. Now, before we move on, it is very important to remember to select your first wall right here. If you forget that step, it will cause all kinds of problems, and it took me quite a while to remember how to fix that. At this point, I will be following the tutorial that is the third in the description almost exactly. So we're going to take a filter, and you can do alphabetical, or you can search for it. We're going to extract a block. So we'll type in, okay, that's not what I wanted. We'll just type extract block, that one. Now in our extract block, now we have the option to select wall. If you forget that first step, it won't give you that option. And that makes it very frustrating because it won't work. And then we'll click apply. Now you can see it has cut out everything that was not part of the wing. It also cut off a little bit of this wing out here, which is annoying. But if you do the whole plane inside, you won't have to do this, or you won't have to worry about it cutting things out. That's part of the reason why I computed the entire plane when I did do that. Now from here we need to extract this surface so we can do operations on that. So we'll click on it again, and then we'll go to filters. You can do alphabetical or search. Either way, we're going to be doing extract surface. And all that looks good, so we'll hit apply. From here we need to generate surface normals. That is another filter, so we'll click on that. Don't forget to select that compute cell normals checkbox on that one. That's another sneaky one that'll cause problems. Now we have a new thing in our dropdown. We can look at normals, and we have these values that are calculated for each cell. It's kind of neat. Looks kind of random, but we're going to do something with that. These surface normals give us a value that we can now calculate lift and drag from. So we're going to click on the calculator icon, create one of these, and we'll call the first one drag. We'll do it backwards from the video. And drag is any force that is going to be acting back, pulling the plane backwards. So the direction that makes the most sense for drag, looking here, it would be the Y direction. So we will do a scalar normals y times, or not minus, times scalar pressure. And then we will click apply. And then we can rename this drag. Oh, and it is a cell data, not a point data. There we go. Don't know why it changed color when I did that, but if we put it back to point data, you can view where the drag is affecting the aircraft. So we have negative drag on the top, so there's almost some forward acceleration pulling the plane forward there, but there's some regular drag on the back, so the back of the wing pulls it back some, and that makes sense just because of the curvature. Front of the wing definitely creates a good bit of drag, and trailing edge should have some as well. Not a whole lot though. And we definitely have some drag happening right at that intersection of the winglet and the wing, which is interesting. That's part of what I was trying to minimize by adding a curve. Moving the whole winglet backwards as Burt Rutan originally designed is another method that also helps minimize that. There are different ways to fix that problem. Anyways, from here we will do we'll put that back to cell data and apply that. We'll make another one, we will do a filter, integrate variables, and we'll click apply. It brings up a nice spreadsheet for us. We'll go over to cell data, and you can see we now have drag. In this case, we have a value of 178 newtons, or I think those are in newtons. And then we can do another one for lift, so we can do a filter, calculator. We'll call this one lift. We'll do it here again. Again, cell data. And lift is anything acting upwards relative to the airstream. So since our airstream was right along the axis, or the y-axis, we'll be doing the z-axis here. Not sure why they have it all rotated down there, but just annoying things that happen when you jump from program to program and have to be ready to deal with that. Stuff gets rotated. Anyways, we'll do our normals, z times our pressure, and apply. Now the lift appears to be behaving. So when I put both of them in there, all of a sudden the cell data started working again. There we go. So I guess I selected the wrong drag. Don't do... That's really weird. That might be a bug. Anyways, when it gives you that error where it all went blank like that, just make sure you have the box with drag selected on it. Anyways, there's our lift, and we can jump back and forth between them and see which one's which. So there's our drag, and there's our lift. You can see lots of lift on the upper surface, and not as much lift like on the leading edge, where we're not doing a whole lot with the air. Which is not doing a whole lot to help lift the plane upwards, of course. There has to be a leading edge. That's just how objects work. And then we will hit filters, and we'll do another integrate variables, and we'll apply that. Look at that. It puts it down here, I guess. We'll make sure this is on cell data. We can see our lift there. We have 1,400, and our drag is 178. That's a pretty big jump compared to what I had before. If I bring over my spreadsheet here from what I had before, at the internal radius of 0, 2-degree angle of attack, I was seeing a drag of 76 and a lift of a little less than that. So these numbers do make sense because I increased the angle of attack to 3, but I left the speed the same. Normally a 1-degree increase in angle of attack would significantly decrease the speed because the plane would be slowing down. And we can see that there's a huge increase in drag when we try to maintain that angle of attack at this speed. That would be like pulling back on the controls. Maybe pulling a few Gs, probably not quite 2, but maybe 1.5 or something like that. And then we can calculate our lift to drag ratio if we want to. And to do that, you'll just open up a calculator. We'll bring it over here. And we will take our drag value right here, we'll take our lift value, and it's just lift divided by drag. It's really quite simple. And this was the number, this lift to drag ratio that I was using to calculate, speed, I think. And then here we have a drag of 178. 0.821. And we have a lift to drag ratio of 7.8. You can see that is significantly less than what we had before, but the main reason for that is we had a pretty aggressive angle of attack for this speed of the airplane. This was the kind of lift to drag ratio we would expect while doing something like a steep turn or a more aggressive maneuver. And yeah, that makes sense. So there you go. That is how you can get the lift and drag, and to get rid of these, we can put those away. And that's how you can do your own computational fluid dynamics study if you really want to. You'll have to make a model or find a model of whatever you want in a step file, and then you can import it into FreeCAD, download the necessary add-ons, and this procedure should work for you. And sometimes, as you can see, you just have to mess with it a little bit, do a bit of digging on the internet, and you can get some results that kind of make sense, or at least work for my purposes. Although those numbers of drag and lift don't mean a whole lot because we have such a granular, not smooth surface, the change in them from one curve of the wing to another, for analyzing the minor changes in an aircraft design, this is a great method, especially when you have those real world numbers like I did to compare them to. So that's how I did it. I'm not saying that this is a how-to, but this is how I did it. This was the process used, and I hope it helps you do the same if that's something you would like to do. So thank you so much for watching. I hope this helps, and I hope you have a very nice rest of your day.